Hello everyone and welcome back to our electronics exploration. Today we are diving into another essential topic, full wave rectification. Before we delve into the full wave rectification, let's take a moment to recall our previous video on half wave rectification. We have learned how a diode allows current to flow in one direction, creating a pulsating DC waveform. Now let's see how we can make this process even more efficient. Unlike half wave rectification, where we only utilize half of the AC cycle, a full wave rectifier cleverly utilizes both half of the cycle to create a smoother DC output. To achieve full wave rectification, we often use a center tap transformer. This transformer provides two secondary windings and each with a diode connected in series with it. During the positive half cycle of the AC input, current flows through one diode. Here you can see current flows through the D1 diode during the positive half cycle and reaches the load. Meanwhile, during the negative half cycle, current flows through the other diode again and reach the load. This means that the output waveform is composed of two positive halves, resulting in a more constant DC voltage. Another popular approach to full wave rectification is using a bridge rectifier circuit. It eliminates the need for a center tap transformer and offers a more compact design. The bridge rectifier circuit consists of 4 diodes arranged in a bridge configuration. Regardless of the polarity of the input AC, 2 diodes always conduct, allowing current to flow through the load in the same direction. During the positive half cycle of the source, diode D1 and D2 conduct while D3 and D4 are reverse biased. This produces a positive load voltage across the load resistor. Note the plus and minus polarity across the load resistance. During the next half cycle, the source voltage polarity reverses. Now, D3 and D4 are forward biased while D1 and D2 are reversed biased. This also produces a positive load voltage across the load resistor as before. Full wave rectification is highly efficient and finds extensive application in power supplies, battery chargers, and electronic devices that require stable DC power. The only disadvantage of the bridge rectifier is that the output is 2 diode drops. That means 1.4 voltage less than the input voltage. Now let's go back to the simulation part. We are going to simulate the full wave rectification, full wave bridge rectifier actually in the Proteus software. Okay, so after opening this schematic capture, we are going to choose this P option here, pick device. Then here inside this keyword we are going to write V sine, and that will give us the AC voltage source, a sine wave for our input signal. And then after that again we are going to pick another device and here write the keyword resistor, and you are going to get a resistor from here. Then click OK. Let's find the capacitor first and add it, and after that we are going to write bridge. And for that you can actually choose this diode option, and inside this you can see the subcategory bridge rectifier. You will actually get a bridge rectifier, all 4 connected together. And if you want to make your own, you can actually get the diodes, single diodes, and connect them together like bridge rectifier connection, and it is also okay. We are going to get this one, and after that press OK. Now all the components are here together. Now we can just click on everything and place where you want to place your rectifier, and then we are going to put the input voltage beside it, and after that the capacitor and the resistor will be on the right side of this bridge rectifier. Let's place them both, and then after that we are going to rotate them. The capacitor, we don't need to rotate it, we just need to rotate the resistance. So for that right click, and here you can find the rotate clockwise. Okay, and now let's connect these sources. Positive will be in this position and the negative will be in this position. Okay, now from here we are going to connect our load. Okay, Okay, connect this wire across the load resistance, and if you want to drag anywhere, you can right click on it and then drag it like this. Okay, so now we need to actually connect the capacitor across it. Connect it from here to this capacitor, because the capacitor will be parallel to the load resistance. And after connecting them, we are going to finally watch the output inside our oscilloscope. But before that, let's correct those values here. 1K will be our resistance and 1 microfarad is the capacitance. Okay, we can actually change the capacitor values to see the output, whether the pulsating DC is actually, whether it is giving pulsating DC or not. Let's give 5000 for now. And here inside the V sign, we are going to give an amplitude of 100. Let's give 10 voltage, and then the frequency will be 60 Hz. Now press OK. So let's give the value of capacitor a bit lesser, because we actually want to see the changes when we give a lower value of capacitor, or what happens if we give a bigger value of capacitor. Now let's click here, and we are going to get our oscilloscope inside our circuit and press here. Now for the channel A, we are going to see our input, and for channel B, we're going to see our output. We just need to select a point where we need to watch our voltage. And after that, we just need to select these buttons, like how we actually changed in our original oscilloscope in the laboratory. And you can actually change the value of this voltage division, and time division will be on the left corner. This is for the second channel, that is our output. You can see the color of the waveform to see check whether it is the input or output. Here all the buttons are actually for different functionalities. You can just test it out if you need these values. See, now we are going to modify the capacitor value and see the output, how it looks like if we give a bigger value of capacitor. Let's give 4000 microfarad, and now we are going to rerun our simulation, and you will see that this is the output that we have seen previously. There was our pulsating DC as the output, but this time we are getting quite close to pure DC value. That is a straight line, right? But you are probably getting confused because of the other two channel. Let me just turn off channel C and D. Now the first channel is our input and the second channel is our output. But here let's see if we actually give a smaller value of capacitor than 4000 microfarad. Let's see, we are going to give here 100 microfarad, and you can see a little portion for charging and discharging, right? If you give more smaller value for capacitor, you will see the charging and discharging time more clearly. Let's give 10 microfarad, and now let's run it. Now you can see the charging and discharging time is visible more clearly. So that is why we are going to give a moderate range or moderate value for this capacitor. We can actually use 100 or 1000 microfarad for this type of circuit, for this amplitude of voltage. And that's how we are going to get a pure DC signal that we can use inside our DC circuit. And this is how we can actually give the direct input to our project. That's all for today. Thank you.